Hi, everybody. What I'm going to talk to you about today is the start of Chapter 3. This is going to be Chapter 3, Video 1, and it is going to go over average atomic mass. So the start of Chapter 3 tells us that chemical stoichiometry is the study of quantities of material consumed and produced in chemical reactions. We're not going to focus on that in this video, but instead, we are going to focus on atomic mass. And so, for example, elements occur in nature as mixtures of isotopes. And if we talk about carbon, carbon is 98.99% carbon-12, 1.11% carbon-13, and less than 1/100th of a percent of carbon-14. And in case you don't remember, the reason why these are isotopes, let's just do carbon-12 and carbon-13. Remember that they have different mass numbers, but the same atomic numbers, and this makes them isotopes. Okay, that's where the isotopes come from. And if we subtract mass number minus atomic number, we get the numbers of neutrons, and each of these has a different number of neutrons. But now, if we want to, we can find out the average atomic mass of this carbon. And in order to do that, we are going to take the percentage times the mass and add it to the percentage times the mass for all of the other isotopes. We get a weighted average because the average atomic mass, also just known as atomic mass, which is found on the periodic table of elements, is a weighted average of the abundances and masses of any of the naturally occurring isotopes. So what we're going to do is just take this mass and for each isotope and multiply by the percent that it makes up of the total, and then we're going to get our average atomic mass for carbon. And that average atomic mass for carbon is 12.01 atomic mass units. And actually, the IUPAC, the International Union of Pure and Applied Chemists, have changed atomic mass units abbreviation to just U. That did happen over the last couple of years. So that's why you'll still see some textbooks and some tables still say AMU. But the proper abbreviation is just U. So again, it is a weighted average. This number is what we see on the periodic table for carbon. And this average atomic mass just tells us, again, the average mass of carbon atoms. There is not a single carbon atom that has a mass of 12.01. But for stoichiometry, because we're going to have such a large sample, a large number of carbon atoms, we can say that this is the mass for stoichiometry purposes because it will be the average mass of all of the atoms present. Now, you might be wondering, how do they know the abundances of the different atoms and what they can actually do? Scientists can use a mass spectrometer, which will actually separate out a sample of a single element. And so once we separate out that sample, we actually collect all of the different isotopes that were in that sample, and we can see their abundances and their masses by looking at this mass spectrometer. Now, type of exercise or a problem that we can do might be asking us, an element consists of 62.60% of an isotope with this mass and 37.40% of this mass, and it might ask us to find the average atomic mass. So if we want to do that, we are going to take the weighted average, not really a lot of space here. So let me just do that up here. So 62.60% times 189. Sorry about that. I copied it wrong. 186.956 plus 37.40% times 184.953. Once I add those two results up, I will get my average atomic mass. So you can just do this on the calculator and get these two numbers. I got this one to be 117.0345. You should be calculating with me. I got the second one to be 69.1724. And then when I add them together, what I get as a result is the average atomic mass. So add those two numbers together and see what you get. I'll wait. Everybody should have their calculator out and should be doing the math problems with me. And the answer that I get is 186.21. And remember, that's in atomic mass units, which is abbreviated as U. So how do we find out what element this is? I'm going to give you a hint. It's right here. We are going to look on the periodic table, which you should have, and on the periodic table of elements, you are going to look for the element that has a mass around 186. I see it, 186.21, and it happens to be number 75, and the element is Re. So that means that this is the element that was being discussed in this problem. And Re is rhenium. Any element, remember, has its average atomic mass on the periodic table. And the way that we find the average atomic mass is by taking the percent abundance times the mass of the isotope and then making that weighted average. Another way to represent percentage abundance would be with mass spec data. So you saw the picture of what a mass spec could look like, but this is just going to give you an idea of what some of that data could look like coming out of the mass spec. So for example, we have this, and I just shrunk me in the corner down there just to make sure you could see the questions. So this is just another way to represent the data. And instead of saying, percentage of, whatever mass and just listing it out, you might need to look at it in table form. And what we can see is that the mass number of 84 has a really, really small relative abundance, but the most prevalent or most abundant isotope is 88. So the whole number that the atomic mass is going to be closest to will be based on these percent abundances. And because there is such a high amount naturally for strontium 88, and again, remember, if you do know the mass number, that would become part of the name of the isotope. So this would be strontium 84, strontium 86, strontium 87, and strontium 88. If we did the percentages times the mass, it's over 80% strontium 88. So we would expect 88 to be close to the atomic mass or average atomic mass of strontium. And if we look on the periodic table, strontium has an average atomic mass of 87.62 atomic mass units. Now, if we just take off some of this information here so you can see this a little bit better. In this sample, do we see evidence of a strontium 85? Well, look, I see strontium 84, 86, 87, and 88. 85 is blank, so that would mean no, there is not an isotope for strontium 85. And if we wanted to write out the mass percent, 84 would probably not really be part of this. We would say 10% of strontium 86. We would say maybe 8% of strontium 87. And also we would add that to what looks like 82% of strontium 88. We would add those three results together. Notice that maybe that means that this is actually more like 83%. This doesn't quite add up to 100, but you would have a table with more defined values if you actually had to come up with this from it. Perhaps we could also look at Mercury's mass spectrum data. And if we look at Mercury's mass spectrum data, we can see that, for example, we have a Mercury 196, 198, 199, 200. Wow, this is a lot of isotopes. 201, 202, and 204. Now, when the mass spectrum comes out, the darkness of the color tells us how much of each isotope is present. So you would see that 202 has the darkest color because 202 is the most abundant. You don't have to memorize this. This is just something that could possibly show up to show you something about the isotopes of an element, and it's always just good to see the different ways that they can represent this. Now, here are all of the natural abundances that relate or correlate to this particular set of data. And what we can see is that we go 196, oh look, no isotope for Mercury 197, 198, 99, 200, 201, 202, and there is no isotope for 203. That means that there is not likely to be a Mercury 203. For some reason, it's just not prevalent or it's just not present in this sample. So we can look and see. We can also take a look at this. And if we were talking about like Mercury 202, we could look up the atomic number on the periodic table. And for Mercury, the atomic number is 80. And again, we would take mass number minus atomic number to get neutrons. Could be something that they might ask. So do the math. 202 minus 80. See what you get. Everybody should be working with their calculator. Chemistry is not a spectator sport. What you see is that that would mean that this particular isotope has 122 neutrons, where mercury 204 means that it has 124 neutrons. So that is the end of talking about the average atomic mass. Again, this was chapter 3, video 1. Please, if you have any questions, either rewatch the video and see if you can find out what you're missing. Ask me a question if you're in person in class. Send me a message on Remind. Send me an email through school email, and I'll help you out. Talk to you soon. Bye-bye.